Hello friends, I am Rose Simon, m.tech student of 𝐂𝐄𝐒 College of Engineering. Now I am going to discuss about test for shear strength. Shear strength is one of the most important engineering properties of a soil because it is required whenever a structure is dependent on the soil's shearing resistance. So what do you mean by shear strength? Shear strength is defined as the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. For the determination of shear strength, we have four tests. First one, direct shear test, triaxial test, unconfined compression test, and Vane shear test. First, we are going to discuss about direct shear test. It is used to determine the shear strength of both coarse soils as well as non-coarse soils. It is quick and inexpensive test. Figure 1 shows the shear box with different porous stones. Apparatus. Direct shear box apparatus. Loading frame that is used to apply vertical load. Dial gauges for measuring horizontal displacement as well as vertical displacement. Proving ring for measuring shear force. Tamper, straight edge, balance to weight up to 200 mg, aluminum container and a spatula. The procedure. Check the inner dimension of the shear box, put the part of the shear box together, calculate the volume of the container and weigh the container. Place the soil in the smooth layer and if you require dense sample, tamp the soil using a tamping rod. Weigh the soil container. The difference of these two is the weight of the soil. Calculate the density of the soil. And make sure the surface of the soil is plain and insert the plain grid on the top of the specimen. Insert the loading block and place the steel board. Remove the shear pin. Attach the dial gauge which measures the change of volume. Before proceeding to test, check all adjustments to see that there is no connection between two parts except sand or soil. Start the motor and take the reading of the shear force and record it. Now set the dial gauges to 0 before starting the experiment. For specified shear displacement dial readings, record proving ring reading. The test is carried out till failure or a lateral movement of 20% of length of the specimen is reached. Next, the calculation of direct shear test, that is normal stress sigma is equal to N by A, where N is the normal force and A is the cross-sectional area. Then shear stress, that is tau is equal to B by A, where B is the shear force or shear resistance developed and A is the cross-sectional area. Next, we can discuss about the results obtained from the direct shear test. Figure 3 shows the stress-strain curves obtained from the direct shear test. Figure A shows the stress-strain curve plot between the shear stress tau and the shear displacement delta H by L. In case of dense sand or over-consolidated clay, the shear strength attains a peak value at a small strain. With further increase in strain, the shear stress decreases slightly and become more or less constant. Also in case of loose sand or normal consolidated clay, the shear stress increases gradually and finally attains a constant value. Then figure B shows the volume change with an increase in shear strain. When we consider dense sand or over consolidated clay, the volume first decreases slightly, but it increases with further increase in strain, and in the case of loose sand, the volume decreases with an increase in shear strain. Next, the figure 3 shows the void ratio of initial loose sand decreases with an increase in shear strain, whereas that for initially dense sand increases with increase in strain. Next, figure 4 shows the failure envelope obtained by plotting the points corresponding to shear strength at different normal stresses and joining them by a straight line. The last result or The last graph obtained from direct shear test is the Moore circle, which represents the failure envelope and minor principal stress and major principal axis. The advantages of direct shear test. Sample preparation is easy. Relatively simple and quick test. Apparatus is relatively cheap. Indifferent strength parameters can determine. It is ideally suited for conducting drain test on cohesionless soil. Then disadvantages of direct shear test. Intermediate stress condition cannot be determined. Stress distribution is not uniform. Orientation of failure plane is fixed as horizontal. Control of drainage condition is difficult. Measurement of pore water pressure is not possible. Reliable mostly for granular soil only. Solved problem. That is, indirect shear test, the failure of soil occur at a shear load of 180 Newton. The corresponding normal load was 360 Newton. Determine the angle of internal friction and principal stress during failure, where C is equal to 0. Given data, shear load tau is equal to 180 Newton and normal load sigma is equal to 360 Newton. We know the shear box is a square box and the area of the square is equal to A square. Therefore, area is equal to 6 into 6, that is equal to 36 centimeter square, that is equal to 3.6 into 10 raised to minus 3 meter square. Therefore, shear stress equal to 180 into 10 raised to minus 3 divided by 3.6 into 10 raised to minus 3, that is equal to 50 kilonewton per meter square. Normal stress is equal to 360 into 10 raised to minus 3 divided by 3.6 into 10 raised to minus 3, that is equal to 100 kilonewton per meter square. Now, we can draw the graph by plotting tau at y-axis and sigma at x-axis for getting phi, sigma 3 and sigma 1. Mark shear stress 50 kilonewton per meter square and normal stress 100 kilonewton per meter square in the graph. From that coordinate, draw a line towards the origin to get the angle. From the coordinate, drop the perpendicular line towards the x-axis and take that line as a radius and draw the circle. Thus we will get the major principal stress sigma 1 as 180 kilonewton per meter square and minor principal stress as 70 kilonewton per meter square. The second test is triaxial test. It is used to measure the shear strength of a soil under controlled drainage condition. This test is called triaxial because the three principal stresses are assumed as controlled. Figure 7 shows the triaxial apparatus. Triaxial loading unit, triaxial cell, proving ring, dial gauge, split mold, rubber membrane unit. Then procedure. Prepare the specimen of the specified diameter with a diameter to height ratio about 1:2. Prepare at least 3 samples under the same condition. Keep the soil sample inside a rubber membrane without any enwrapped air. Fix the specimen on the pedestal of the triaxial cell by keeping a plain metal disc at bottom of sample and fix the O-ring into the pedestal. Place the loading pad onto the top of the specimen and connect the pressure unit to the cell to apply the desired lateral pressure 1 kg per centimeter square. Start axial loading immediately. Take axial load reading and the deformation reading at failure of the specimen. Repeat the test 2 or more times with identical specimen for different cell pressure 2 kg per centimeter square and 3 kg per centimeter square. Then draw most stress circle for each test result. Find C and phi from the shear strength envelope. Then the figure 9 shows the simple structure of the triaxial apparatus with a drainage valve and a pressure meter to measure the pore water pressure. The cell is filled with a fluid which will exert a confining pressure to the soil, and it is known as sigma C or sigma 3. and a deviated stress is applied vertically and it is known as sigma d. Therefore, the total stress sigma 1 is equal to sigma 3 plus sigma d. According to the drainage condition, triaxial test can be divided into three tests such as consolidated drain test, consolidated undrained test and unconsolidated undrained test. Now we are going to discuss about consolidated drain test, that is CD test. It is called as slow test, then it can be abbreviated as S test. Drainage valves open during consolidation as well as shearing phase. Load is applied at slow rate that the particle readjustments do not induce any excess pore pressure. Since there is no excess pore pressure, total stresses will equal to effective stress. These tests simulate long-term shear strength for cohesive soil. Now we can discuss about the results obtained from consolidated undrained shear strength test. Figure 10 shows the stress strain curve for drain test. And first two figures shows the stress strain curve for drain test with deviated stress at y-axis and axial strain at x-axis. For dense and over-consolidated clay, the sigma d reaches a peak value and then it decreases and becomes constant equal to ultimate stress at larger state. For loose sand and normally consolidated clay, the deviated stress increases gradually till the ultimate stress is reached. Then figure 3-4 shows the volumetric strain. In dense sand and over-consolidated clay, there is a decrease in the volume at low strains, but at large strains, there is an increase in the volume. In loose sand and normally consolidated clay, the volume decreases at all strains. Then the figure 11 shows the type of effective stress failure envelope obtained for tests on sands and normally consolidated clay. And the figure 12 shows the failure envelope obtained from drain triaxial test. Next is CU test, that is consolidated undrained test. In this test, drainage valves open during consolidation phase but close during the shear phase. Pore pressure develops during shear and the test can simulate long-term as well as short-term shear strength for cohesive soil. The results obtained for CU test is similar for consolidated undrained test. Figure D and E shows the stress strain curve for a consolidated undrained test. The shape of the curve is similar to that obtained in a consolidated drain test. And in the figure 14 shows the variation of pore water pressure with axial strain for sand and clay. That is, F and E shows there is an increase in pore water pressure throughout for loose sand and normally consolidated clay. The next is figure 15 shows the Mohs circles at failure obtained from consolidated undrained triaxial test in sand and normally consolidated clay. And the figure 16 shows the total stress failure envelope obtained from consolidated undrained test for over consolidated clay. Next is unconsolidated undrained test. It is also that is UU test. It is also called as the quick test. Then it is abbreviated as Q test. Sigma 3 and delta sigma are applied fast, so the soil does not have time to settle or consolidate. Drain valve close for all phases at the test and test simulates short-term shear strength for cohesive soils. This figure shows the failure envelope in terms of total stress obtained from an unconsolidated undrained test on a normally consolidated clay. The failure envelope is horizontal, that is pi equal to 0 and has a coefficient intercept of Cu. Then the advantages of triaxial shear test. The stress distribution on the failure plane is uniform. The specimen is free to fail on the weakest plane. There is complete control over the drainage. Pore pressure changes and the volumetric changes can be measured directly. The state of stress at all intermediate stage up to failure is known. The Mohs circle can be drawn at any stage of shear. This test is suitable for accurate research work. Next, disadvantages of triaxial shear test. The apparatus is elaborate, bulky and costly. The drain test takes place a longer period in comparison with test. It is not possible to determine the cross-sectional area of the specimen at larger strains. The strain conditions in the specimen are not uniform. The consolidation of the specimen in the test is isotropic, whereas in the field the consolidation is generally anisotropic. The tests simulate only asymmetric problems. Then the problem from the consolidated undrained test. The following results were obtained from a series of CU tests on a soil in which the pore water pressure was not determined. Determine the shear parameters. For sample 1, confining pressure is equal to 100 and deviator pressure is equal to 600. And for sample 2, confining pressure is equal to 200 and deviated pressure is equal to 750. And sample 3, confining pressure is equal to 300 and deviated pressure is equal to 870. We know principal stress sigma 3 is equal to sigma c, and for major principal stress sigma 1, that is equal to sigma c plus sigma d. Therefore, major principal stress for sample 1 is equal to 100 plus 600 is equal to 700, and for sample 2 is equal to 200 plus 750 is equal to 950, and for sample 3 is equal to 300 plus 870 is equal to 1170. For finding C and phi, we are going to draw the graph with tau at y-axis and sigma at x-axis. For drawing the Mohs circle, we need to find the center of the circle. Thus, we have to find the average of the two stresses, that is minor principal stress and major principal stress. Therefore, 700 for sample 1, 700 plus 100 divided by 2 is equal to 400, and for sample 2, 950 plus 200 divided by 2 is equal to 575, and for sample 3, 1170 plus 300 is equal to 735. Now place the compass needle at the center and take the radius from this point to the minor principal stress and draw a semicircle. Then draw a tangent line for these three circles. This slope will give the phi value and height will give the c value. Next, the third test for measuring shear strength is unconfined compression test. It is the most common, cheap and fastest method for soil shear testing. It is a special type of unconsolidated undrained test commonly used for clay specimens. The unconfined test is used for corrosive saturated soil. This test is inappropriate for dry sand or crumbly clays. This is essentially a special case of the triaxial compression test where the minor principal stress is 0. Next, the apparatus: UCC testing unit, proving ring, dial gauge, split mold, soil sample and frictionless end plates. Procedure for unconfined compression test. For the desired water content and dry density, calculate the weight of the dry soil required for preparing a specimen of 3.8 cm diameter and 7.5 cm long. Add required quantity of water to the soil. Mix the soil thoroughly with water. Place the soil in a constant volume mold having an internal height of 7.5 cm and internal diameter of 3.8 cm. Apply the compressive load till the specimen is compacted to a height of 7.5 cm and eject the specimen from the constant volume mold. Then take two frictionless bearing plates of 75 mm diameter. Place the specimen on a bearing frame and place a hardened steel ball on the bearing plate. Adjust the center line of the specimen such that the proving ring and the steel ball are in the same line. Fix a dial gauge to measure the vertical compression of the specimen. Adjust the gear position on the load frame to give suitable vertical displacement. And start applying the load and record the proving ring reading corresponding to specific deformation shown by dial gauge. Then compress the specimen until failure is complete. Continue loading till failure is complete. Sketch the failure pattern and take a sample for the determination of moisture content. Then the maximum value of the axial stress is the unconfined compressive strength of the sample, that is QU. Then the calculation, that is shear strength of soil, is equal to QU by 2, where QU is equal to unconfined compressive strength. Then the result. Figure 20 shows the stress strain curve obtained from the unconfined compressive stress, where stress in the y-axis and axial strain in the x-axis. The graph shows an increase in the strain and gradually, and after a peak point it decreases and becomes constant. Figure 21 shows the Mohr circle drawn for stress condition at failure obtained from the unconfined compression test. Then the advantages of unconfined compression test. It is convenient, simple and a quick test. Ideally suited for measuring the unconsolidated undrained shear strength of saturated clay, and the sensitivity of the soil may be easily determined by conducting the test on an undisturbed sample and then on the remolded sample. Then the advantages of unconfined compressive test. It cannot be conducted on fissured clay. The test may be misleading for soils for which the angle of shearing resistance is not zero. For such soils, the shear strength is not equal to half the compressive strength. Then the problem. In an unconfined compression test, a sample of clay 8 cm long and 4 cm in diameter fails under a load 120 Newton at 10% strain. Compute the shear resistance taking into account the effect of change in the cross section of the sample. That is, given data, D naught is equal to 4 cm, that is equal to 40 mm, L naught is equal to 8 cm, that is equal to 80 mm, epsilon equal to 10%, that is equal to 0.10, and the load P is equal to 120 Newton. Therefore, A naught is equal to pi by 4 into 40 square, that is equal to 1256.63 mm square, and AF is equal to A naught divided by 1 minus epsilon, that is equal to 1256.63 divided by 1 minus 0.10, that is equal to 1396.26 mm square. Therefore, unconfined compressive strength QU is equal to sigma 1, that is equal to P by AF, that is equal to 120 divided by 1396.26, that is equal to 0.086 Newton per mm square, that is equal to 86 kilonewton per meter square. Therefore, shear stress at failure C is equal to QU by 2 is equal to 86 by 2 is equal to 43 kilonewton per meter square. Now, the last test for measuring the shear strength, that is Vane shear test. It is used to find the shear strength of the soil, that is applicable to soil undrained strength less than 200 kilopascal, and the test can be conducted in field as well as in. It can be easily used to determine the sensitivity of a soil. Figure 22 shows the Vane shear blade that is used in the Vane shear apparatus. Vane shear apparatus of soil specimen, specimen container, vernier caliper and sensitive weighing balance. Now the procedure of Vane shear test. Clean the Vane shear apparatus and apply grease to the lead screw for better movement of handles. Then take the soil specimen in the container, which is generally 75 mm in height and 37.5 mm in diameter. Then the application of torque can be done using springs of different stiffness. To start with, the springs of stiffness is attached to the Vane shear apparatus, and level the soil surface on the top and mount the container on the base of the Vane shear test apparatus using screws provided. Lower the vane gradually into the soil specimen until the top of vane is at a depth of 10 to 20 mm below the top of soil specimen. Rotate the vane inside the soil specimen using torque applying handle at a rate of 0.1 per second. And when the specimen fails, the strain indicator pointer will move backwards on the circular graduated scale, and at this point stop and note down the final reading of pointer. Then the difference between the initial and final reading is nothing but the angle of torque. Repeat the procedure on 2 more soil specimens and calculate the average shear strength value. Measure the diameter and height of vane using vernier caliper. Sensitivity of given soil sample is determined by repeating the above test procedure on remolded soil, which is nothing but soil obtained after rapid stirring of vane in the above test. Next, the results. Undisturbed shear strength value is equal to T by pi into d square h1 by 2 plus dq by 6, where T is the torque applied in Newton centimeter and D is the diameter in centimeter, h is the length in centimeter. Therefore, sensitivity is equal to shear strength value of undisturbed soil divided by shear strength value of remolded soil. Advantages of Vane shear test. The test is simple and quick. It is ideally suited for the determination of the undrained shear strength of non-fissured fully saturated clay. The test can be conveniently used to determine the sensitivity of the soil. This test can be performed either in the laboratory or in the field directly on the ground. Shear strength of the soft clays at greater depth can also be found by Vane shear test. Next, the disadvantages of Vane shear test. It is not suitable for clays which contain sand or silt laminations in it. It cannot be conducted on the fissured clay. If the failure envelope is not horizontal, it does not give accurate results. Problem. A shear vane 7.5 cm dia and 11 cm length was used to measure the shear strength of a soft clay. The torque required for the failure of the soil in natural state was 600 Nm and that required for the remolded state was 200 Nm. Comment the sensitivity of the soil. Therefore, given data D is equal to 7.5 cm, H is equal to 11 cm, T is equal to 600 Newton per meter and S equal to T by pi into D square H1 by 2 plus dq by 6. Therefore, stress at natural state is equal to 600 into 10 raised to minus 3 divided by pi into 0.075 square into 0.11 divided by 2 plus 0.075 cube divided by 6, that is equal to 503.08 kilonewton per meter square. Stress at remolded state is equal to 200 into 10 raised to minus 3 divided by pi into 0.075 into 0.11 divided by 2 plus 0.075 whole cube divided by 6, that is equal to 167.66 kilonewton per meter square. That is equal to undrained shear strength value of undisturbed soil divided by stress at remolded soil, that is equal to 503.08 divided by 167.66, that is equal to 3. Therefore, the soil is moderately sensitive. Thank you.